Hello everyone, welcome to this channel. Today we are going to talk about a highly theoretical physics problem. But trust me everyone, you don't really need to solve the quantum mechanics question or use Maxwell equations. All you need is nothing more than A-level physics knowledge. So everyone, here's the problem. If we look at our Earth as a uniform and solid sphere, which will be our assumption in this problem, and we'd like to drill a tunnel through the center of the Earth, which will also be straight. So if I drop one mass at one end of the tunnel, and we want to know how long it is going to take for the mass to reach the other side of the tunnel. As usual in this video channel, I'd like to talk through some prior knowledge before we actually enter the question. First of all, let's just consider the surface of a hollowed sphere. Here, I'm going to show you a simple proof that if you put any mass inside a holosphere, the holosphere is not going to exert any gravity on it. Obviously, I'm producing a hand-wavy argument here because this is not the main show of this video. If you are interested in how this is actually proved, please check the video link below. Now, I would like to draw two lines across the point in the sphere. As you can see in the diagram, the point is subtending two arcs, which are actually two surfaces, but you can't see it because we draw the diagrams in two dimensions. Each surface is exerting gravity upon the point inside the sphere, and let's just write that as F1 and F2. And also we use A1 and A2 to denote the area of both surfaces. And we say D1 and D2 are the distances between the point in the sphere and the centers of the surfaces. Now, I'm trying to work out the relation between the distances from the point and the area of those surfaces. According to geometry, we know that the relation between the distance and the length should be linear. However, A1 and A2 are two surfaces, which will be the square of the length. So we know that A1 will be proportional to the square of D1, and A2 will be proportional to the square of D2. Therefore, we can write down A1 over A2 equals to D1 squared over D2 squared. Okay, so now we are moving on to the force equation. We know that the force equation for gravity is F equals to Gmm over R squared. So in this case, we assume that there is a uniform surface density, sigma. So the mass of the surface A1 should be A1 sigma, and that for A2 will be A2 sigma, and they will be the bigger m in the force equation. So with that in mind, we can write F1 equals to G A1 sigma m over D1 squared, and F2 equals to G A2 sigma m over D2 squared. In order to equate F1 and F2, I need to do a slight change for the first equation. If I rearrange that, I can write it as A1 over D1 squared equals to A2 over D2 squared, and they will be equal to K. If we put it back to the force equation, we can write F1 as G sigma mk, and F2 can be reduced to G sigma mk as well. So you can see that F1 is actually equal to F2. We know that the point was randomly chosen in the sphere. We know that these two dashed lines were also drawn randomly. This means for any point in the sphere, two opposite surfaces are going to pull the point equally, which means gravitation will be cancelled out by each other. Okay, that's all for the prior knowledge, and let's move back to the actual question. We are going to treat the Earth as lots of concentric spherical surfaces. As moving down, we know that the outer shells, like outer spherical surfaces, are not going to exert any force. It's actually what's below will exert a gravity on the mass. Let me be more clear with what I said just now. If I draw the cross, which will represent a point mass here, the spherical shells above it are not going to exert any force. This is because they can be treated as lots of spherical hollow surfaces, and we know that each of the surface will not exert any force on the mass. Since there's no force from any surface above, we know that all the surfaces above will not exert any force. For what's below the point mass, the shape doesn't really matter. This means all masses can be considered to be concentrated at the center, which allow us to use the formula F equals to gmm over r squared to calculate the gravity attraction. Now, let me be clear with what each letter means in this formula. We know that F is the force from the center. Smaller m means the mass of the point mass, which is the cross I drew in the diagram, and bigger M means the mass below the point mass. We can notice that the bigger M is varying all the time when smaller m travels further down into the center. And the smaller r at the bottom of the fraction is the distance between the point mass and the center of mass of the Earth, which is written as COM in the diagram. As I said just now, m is a variable. The smaller r is also a variable. To simplify everything, it will be good if we can write the bigger m in terms of r, so there will be only one variable in the formula. To achieve that, we can first introduce volume to the bigger m. So m can be written as rho times v. We know that v is the volume of the inner shells, which is a sphere. So v equals to 4 pi over 3 r cubed. If we substitute everything back into the force equation, F equals to g times 4 pi over 3 r cubed times rho times m over r squared. Since we have r on the top and the bottom of the fraction, they can be cancelled out. So everything left behind is 4 pi over 3 times g times rho times m. This formula now gives us the size of the gravity, but we know that the force is actually a vector, so we need to write that in the vector form. We also know that gravity is an attractive force. This means it will always point in the opposite direction of the displacement r. So F equals to minus 4 pi over 3 g rho mr. By looking at this formula, some of you may notice that the force is proportional to the negative displacement. We know that this type of force is going to create simple harmonic motion. Just a reminder of what's happening in this video. We are looking for the time taken for a mass to travel from one side of the Earth to the other side. Now we know that the motion is going to be simple harmonic motion, so this is going to save us lots of time. If we divide the force equation by m on both sides, that's going to give us acceleration. If you have your A-level formula sheet at hand, please have a look at it. I believe it will tell you that acceleration can be calculated as negative omega squared times r. And we know that the period of the motion is going to be 2 pi over omega. So if we put the second and the third equation together, we will get 4 pi over 3 g rho equals to omega squared. So we can calculate omega by taking the square root of it, which will be square root of 4 pi over 3 g rho. Also, we know that the time taken for us to go to the other side of the world is going to be half of the period of the simple harmonic motion. So time equals to half t, which will be pi over omega, and we just need to put omega in. Notice that rho is the density of the Earth. We know that the Earth is not uniform, so I take the density of the Earth as the density of rock, which will be 6,000 kilograms per meter cubed. That will give us around 40 minutes for the final answer. Some of you may notice that it is almost the end of the video, but does that mean it's the end of the question? No. If this is the end of the video, it will be the same as any other video you can find on YouTube. What I'm going to do now is going to talk about a harder version of this question, in which the tunnel stays straight, but it will not go through the center of the Earth.